welcome to this session. Thank you for joining us at the Learning Jam. We're super excited to have you guys here. This is going to be a really fun session with Ben. Before we get started, would love to know where you guys are joining in from. I can see the ticker going up. We're about 100 people right now. You can put it in the chat. Tell us your name. Tell us, which city you're joining in from, which grade level you teach. Would love to know all of that. I can see Kurita from Jakarta has joined in. Hi, Kurita. Zeba from India. Danielle from South Africa. We have Lizzie from Malaysia. Oh, hi, everyone. It's always great to see where everyone is joining in from. Makes you feel a little bad about not being able to travel, but that's okay. Um, Great. So I'm just going to move ahead. As people join in, you guys can keep putting your names in the chat. Very quickly, a little bit about Toddle. So Toddle is a one-stop solution for all things PYP and MYP. And Toddle has organized the Learning Jam today. So you can do everything from curriculum planning, projects, portfolios, assessments, reports, family communication, everything from one platform. As educators ourselves, we truly believe in the power of lifelong learning. And so we are committed to doing a lot of, just give me 1 second. So we're committed to doing a lot of different events and different initiatives. We did the Inquiry Educators Summit when the pandemic started, and that was attended by over 30,000 educators from around the world. The Learning Jam is another step in that direction to support educators like you with lifelong learning opportunities. I'm going to try sharing my screen once more so we can quickly go through some housekeeping points. Just give me 1 second. Let me know when you can see. You guys can see, right? Cool. So Ben can't hear you. Jonathan, Catherine, Sonia, all of us can't hear you today. So make sure that you type your questions under the questions tab on the right of your screen. At different times, actually throughout this session, Ben is going to ask you to do a lot of things and think with your hands. So make sure that you're participating, sharing your experience in the chat. The chat is usually where a lot of rich learning unfolds. So make sure to reply to all panelists and attendees. If you only reply to all panelists, we'll be the only ones seeing your chat. So make sure it's all panelists and attendees. We will not be using the raise your hand feature today. So make sure that you don't click on that. It'll all be in the chat or in the Q&A. And finally, a very big thank you to Ben for doing this. We're really excited to learn with you, Ben. And a big thank you to all of our participants who are on the panel today. So Jonathan, Kate, Sonia, really excited to have you guys here. We can start with like quick introductions of everyone and then kick off the session today. Ben, do you want to go ahead and introduce yourself and then?
Sure, I wasn't too sure who could go first, but look, I'm really looking forward to this session. I know it's an hour, but my gosh, it's going to go quickly. We've got so much to do, we really do. But it's not just about me, we do have some other people involved as well. So I might throw to Catherine to say hi.
Hi, I'm Kate O'Connell, and I am the head of school of the Giving Tree International School in Phnom Penh, Cambodia. I am an American and an IB workshop leader, and I also do workshop leading for Compass Education. So if you were in the previous session with Lawrence, then you know what the Compass is now. Great to be here with you, Ben. Thank you for having me.
I'm really excited. Hey, Sonia, say hello.
Hi, namaste from India, and guys, welcome all those who are joining. And yeah, I'm Sonia Kedia, and I'm the PYP coordinator at a school in Mumbai, JBCN International School. And a little nervous, but yeah, I'm sure that we're going to have fun because a lifelong learner. And thank you, Ben, for having us. And you know, I hope I live up to the expectations.
I'm sure it'll be fine. No high expectations here. It's quite okay. Hey, Jonathan, you want to say good day?
Hey, I'm Jonathan. I'm a PYP coordinator from Ascend International in Mumbai. And yeah, I'm just here to have fun. I'm here for the giggles and the science.
Good, you're at the right place. Excellent. That's exactly what this is about. Now, Hector and Parita are helping in the background. I know Hector's certainly dealing with a lot of Q&A behind the scenes, and Parita's making sure the screen moves and looks at people at the right time at various different points throughout this hour. Now, what on earth have you signed up for? So really quickly, my name's Ben from Fizzics Education. We're science outreach people. I'm a former high school teacher, gosh, about over 20 years ago. But we've been doing lots and lots of outreach to hundreds and hundreds of schools every year across Australia, and also been doing distance learning around the world for the last 10 years. And the session today is really just about kind of having some fun with just some science experiments that we know actually works in an online environment, looking at what, not just the experiment itself, but how to make it visual and vibrant and well framed in your screen and all that sort of thing. Now, if you have materials nearby, I know not everyone's going to have it, but in case you're wondering, well, what on earth, I've lost the link or something like that, I'm going to quickly just put that in the chat there. That is the link for all the different materials. Now, don't stress, don't worry if you don't have all the materials. Those materials are linked with a bunch of experiments underneath, which will keep you busy afterwards. The chances are we are not going to cover everything. It's not going to happen. I usually try and put more than we can possibly do in this session. So that, we just don't sort of stop. Now, here's the thing. It is going to cover movement, forces. We're going to do some kitchen chemistry. We might do some stuff on heat. But if you've got a particular area of science that you're really like going, look, I'd love to, just a couple of different ideas about teaching science in this area, please throw that in the chat, because even if I can't answer it, someone in this group, and seriously, there are a couple of hundred of us, someone will know an experiment to help you. So, oh, there you go, straight away. Kalyani was fast. There's biology, fantastic. We'll get to that straight away. Actually, biology is missing in this particular one, except for one little part about 3 steps in. So, tell you what, I will get there. Tell you what, how about we do a quick experiment, which is all about guessing, and more importantly, getting the students to kind of start thinking about, well, what they really actually know. So what I'm going to do is I'm going to change my view. I'm going to go down to over near my hands, down here. I'm going to move my keyboard out of the way, and I'm going to get some water. Now, we haven't got this within your materials. Now, I know it's slightly blurry because it sometimes stresses if you're really, 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 really close to the view. So I'm going to change my view just to a different view like that. Then fine, I'll go with that. Okay, I'll go in close soon. Right, water. I have here a cup and a ping pong ball. So just a simple thing, in it goes. Now, I want to see what you guys think in the chat, and we're going to get like a lot of different answers. We could probably use polls, perhaps, would be probably wiser, but for now, I can put the cup over the ball. I can push down. Now, the ball will have 3 choices. The ball could stay at the top of the water, it could go to the middle of the water, or it could go to the bottom of the water as I push the cup over the ball. So here's your chance to kind of have a guess. What do you reckon? So what do you reckon? Bottom, top, middle. So B for bottom, T for top, M for middle. Here we go. We've got some bottoms, we've got some tops, we've got some middles, we've got some tops, we've got some middles. And off we go with 200 people writing it. It's crazy. So we've got lots of different ideas. Let's see what happens. Now, remember, this particular session is about sort of the middle school years, the way they think. Let's have a look. So I'm going to go in close. Oh, I'll do it while it's not, I don't want to mess around with the blurriness too much. Let's go. Let's see. In we go. I might go really close now so you can see what's going on. So you can see I'm messing stuff up. There we go. Down we go again. Okay. You know what? You kind of could have had 2 answers that are right. It is on top of the water. It's still on top of the water. It's still on top of the water. It's on top of the water no matter where I put it. And the kids might have said bottom of the water. I suppose when I pushed all the way down, I did that too. It all depends on what your vocabulary is, the way you say it. But the answer is that the ball is constantly on top of the water. Why? Yeah, the air's in the way. Air takes up space. And you might notice that as I push down, the water rises. We call that displacement. Up it goes. And it's a nice, easy one to look at. I just go so you're not just talking to my hands. It's a nice, quick one to look at that. yes, we're often looking at the science. Yes, we could be looking at buoyancy or density or whatever fancy science word we want to have. But try and think about what are the kids coming into your lesson with? What misconceptions, what preconceptions will they have? And what language will they use? Because some people who said top could have thought the cup cuts through the water and the ball stays at the top. Others could have said it's on the top of the water no matter what, because you're putting the surface of the water down with the cup no matter what, and the ball just follows the surface always. So just a bit of a, there's really just a heads up that language does matter with it. So yes, the air was in the way. The air takes up space. Now, in case you've got younger ones, or if you get moved to really young students, I saw a couple of people teaching grade ones. There's something that can show, it looks like a magic trick. I'm gonna be honest. So I'm gonna go in close. What you can do, I'll go in close, nice and close, please. It'll be lovely. Okay. So you get yourself tissue paper. Push it in, get a kid to touch it so they can tell it's dry. Push it in, and all you do is repeat the experiment. Now, word for the wise, push your thumb in so it doesn't fall out, and make sure they can't see you doing it, because it tends to fall out. But you do the same thing. Down, push, swish it around, take it out, and oh, it fell out. So thumb falls out. There you go. It stayed in there for as long as possible. The top is still dry, but the other bit's wet because it fell out. Nice, easy thing. Air takes up space. So the thing about air is it's three-dimensional. It's hard for kids to get their head around a spatial, invisible thing. So here is an experiment which some of you will have the materials for, and I suggest you don't do it near your computer, your iPad, your Android device, or anything like that, because we're going to do an upside down water cup. So we're going to do a roll call of materials. You're going to need some sort of bucket. In this case, this is going to be my bucket of water, some sort of something to catch a mess. We are going to need, well, a cup. I'm going to start off with a small cup for a start. I'm going to do like the cheats little one, the baby one, little cup. We're going to need a, whoa, dropping on the floor, a piece of paper. And that's it. Now, what we need to do is, again, not near your computers, because we don't really need to wreck it at the start of the year, but we're going to get our water all the way to the top. We're then going to put our paper on top. There we go. Over the bucket in case you make a mess. We're going to put our fingers on top. Gently press, don't bend the paper, gently press, turn it around. Now, when you turn it around, you often have it dribble slightly. Around we go. And we will take it out, done. Has anyone achieved it? Has anyone got it going? More importantly, does anyone know why this works? I'm going to turn this around. I'm going to do a larger piece of paper, because otherwise, a larger cup, otherwise you might be feeling like I'm cheating or something like that. But why does this work? I'm going to get a cup. I've got lots of cups and things over here. And I'm going to get a piece of paper and I'll cut it again for a larger size. Why does the upside down cup of water work? Now, we had an answer, pressure. Yes, it is about pressure. So my question to you is which sort of pressure are we worried about here? The air pressure or the water pressure? What do you reckon? As I cut a piece of paper off. What do you think? Yes, air. Air pressure is stronger than the water pressure. Yes. Now you kind of, yes, air pressure. Yep. And yes, yeah, I'm just reading all the different answers coming through. So let's do this again. When you do the larger cup, let's be honest, you're more likely to mess up. If anyone's doing this back where you are, let us know how you go, because we can't see you, but it'd be always nice to know how you're going with it. Now, get it pretty much full. Paper on top. Now, try not to get the paper too big, much larger than your cup, or it tends to be too large. Now, the way this works, now you watch me mess this up, but here we go around again. The way this works, oh, it's dripping. It bent. But the way it works, when we go around like that again, air here is pushing up. It holds the cup up. I mean, I'll get my smaller cup here for now. That's why we at least get one, so we don't totally mess it up. Around we go, done. All right. The air here has lots more pressure than the weight of the water. Trying to get your head around the air has pressure is kind of hard, but a good way for kids when they're young is look at your thumbnail. Oh, there you go. Everyone, look at Catherine. Catherine nailed it. We'll have to just swap our thing, but Catherine's got it. And there's a very good, Ben, I did it better than you. And she did. Good job. Great job.
Thank
Is
you.
your water all the way to the top?
There's about a centimeter of no water.
Yeah. I was going for gold with a large cup. But yeah, so that's it. So there's not much water pushing down, and there's a lot of air pressure coming up. So looking at Catherine's yellow card there, you could fit a lot of thumbnail spaces, like thumbnails being a measure of area underneath the paper. Now at sea level, you have the equivalent of 1 kilogram pushing on your thumbnail, give or take, for a square centimeter. It's about a square centimeter. There's a lot more pressure going up than water pressure going down. And it's a nice, fun little experiment for kids to do, especially on a Friday afternoon on a hot day outside. It just works really well. Okay, let's do another one. So the idea of this particular experiment is about pressure. Air moves from high pressure towards low pressure. Okay, let's do one. Now we had a question before, can we do something on biology? So I am going to do something on biology, and it's related to pressure. Now it's going to be one which you can make. Honestly, you'll have to do it afterwards because it takes a little bit of time to mess around, and we want to get through a lot of experiments for you today. We're going to show you how to make a very simple lung model. So I'm going to make the view very low. There we go. Look at this. And it's blurry again. Come back. Okay. What I've got is a bottle, and the bottle has been chopped. And on the end of the bottle, we put a balloon. And the balloon has been chopped so I can fit over the bottle. That's what it is. It's like it's empty there. Now let's look inside of what we've done here. I've got a balloon, a rubber band, a straw, and with some scissors, I just pushed it through the top of the cap. Now, if you wanted to, you could have a join and have a second tube and another balloon if you wanted to have two lungs. But for now, we're going to look at mechanically how your lungs actually breathe, how they work. So we'll tie it up tight. There we go, done. And I'll put it in the way so you can see what's going on. This part here is your diaphragm, the muscle underneath your lungs. So if I push it up, the balloon sort of squishes. If I go down, it opens. Squish, open, squish, open, squish, open. All right, so does anyone know, I'll just go this to my face for now. Why does this work? I know you want to write pressure. You're allowed to write pressure, but how does pressure work for this? How does this work? If I do this, it totally works. Why does this work? When I pull the diaphragm down, the balloon gets bigger. And when I let it go, the balloon gets smaller. How does this actually work? Now, let's be honest, there's a lot of typing involved. So you might have to write a paragraph. I don't know. Pulls air into the straw. There is air in the bottle. True, there is. Air displacement. Air inside the container squeezed the balloon. Yep. That's actually true when I pushed up. So when I push up with the balloon, it squishes on the balloon because it's squishing on the air inside the bottle. When I open up the diaphragm, when I pull the diaphragm down, it opens a space in the bottle, and air always tries to fill spaces. The air here got pushed from more air into less air, from high pressure into low pressure. It was trying to fill the space. It's very easy to make, and it does look at the way you breathe. When you breathe in, your diaphragm goes down. You open up a space in your chest cavity, and air rushes into that space. It tries to lower the that low pressure brings the air in, which is good fun. So yeah, reading through these, yeah, increases the volume. That's it. Decreases the air pressure. That's exactly right. Spot on. Now, bear with me if I don't read your one out because there's lots of people writing. But yeah, and the air compressors are pushed back up. Absolutely. Now, we're going to, again, move through lots of different things. Now, if you're wondering, and I'm just going to sort of pause for a moment, there are a lot of things we could cover in a session like this. I want to make sure that when you walk out of this session that, yes, you've got some a whole bunch of things to work with. I'm going to quickly put this into the chat for everyone. Please click on that link and use it. There are 150. In fact, there are 200 experiments on our website. They're free. Just go to local shops and pick up the materials. Go for it. Use it. Okay, so let's keep going. I had a question about light. Now, I was just thinking, it was less planned, but I do know just off the side over there, there is some what I call fireworks glasses, and I can set my camera up to do something really fast. Okay. All right, so I have to go get them. Right, here we go. Yeah, we got them. So these are fireworks glasses. You might see these in New Year's Eve, and you see people put them on and they can see rainbows all over the place. The problem is that you can't see them from where you are. So a lot of this was talking about how can you teach through online. So what I'm going to do is unplanned. I'm just going to make my camera look straight up at my ceiling at one of my lights. So up we go. Up, 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 up. Oh, too far. Yes, I have foam ceiling on my ceiling. We're going to go look at that light. Wrong way. Other way, other way, other way, other way, other way. Done. Right. So there's the light. Now I'm going to walk up to my camera and I'm going to get a blurry green thing in front of it now. There it is. I'm going to find where it is. Done. And now I'm going to put the light, the glasses in front of it. Look at that. Now you can get fireworks glasses for about $1. Depends on where you find them. But what it does quickly show is that white light is made of all the colors that you can see: red, orange, yellow, green, blue, indigo, violet. And it works incredibly well. In fact, if I just go quickly back to my face, just for now, so I don't have to Google it and slow you guys down, look at it after the session. You can find some color mixing apps where you'll have the primary colors of light, red, green, and blue, and you can mix these circles of light together, and then you get the secondary colors and tertiary colors and so on, and it works. Another way, though I haven't got it prepared because there's only so many things we could do, is I have in this room set this up where in front of my whiteboard, so here, I'd have, honestly, spotlights coming to my whiteboard. And you put red, green, and blue, and it works. Yes, it does work like the prism experiment, totally so. So you can mix light. In fact, what also works quite well is if you can go to your science suppliers, you can usually find a very cheap laser, like a red one, and you can put it through plastic acrylic, and you can look at the links, look at the laser following the plastic acrylic, just like what happens with fiber optics. It follows it, it bounces inside it. It's kind of cool. Anyway, I go off on a tangent. We've got a lot to do. Now, I know a lot of people here have prepared a lot of chemistry stuff. So let's do a little bit of chemistry, hey? So let's do it. We're going to change my view. Now, unfortunately, or maybe it is fortunate, it's up to you, however you feel like it, you're going to be looking at the desk. We're changing our view. There it is, there. Because we're going to do some above view experiments. I'll show you how I've done this setup too, by the way, in case you haven't used multiple cameras. But get yourself a bowl, a shallow plate, something like that. And I can see Jonathan, Sonia, and Catherine, Kate scrambling to get their bits. Yes. Now I'm feeling like we should do, let's do the milk one. I'm going to pour in this case, I'm using full cream milk. In fact, if you're going to do true variable testing, go for full cream, light milk, soy milk, all sorts of stuff. For now, just for speed, I'm doing the full cream milk. Now, all you need to do is cover the base of your, well, thing, your bowl. Now, you can actually see that my bowl is slightly at an angle because my trestle is slightly at an angle and the liquid's pushing off to one way. But that's okay. Now, at this point, we need some food colorings. I've got a couple here. And I do have pipettes. You don't have to use pipettes. You may have some other bits of food coloring around. But for now, I must say, a lot of the kids will always want to add too much food coloring. You just need a dot, just a little bit. Try to tell them, well, ask them nicely to use only a little bit. And let's be honest, there's always that child that doesn't listen and then uses a whole heap. What you're going to do is you can put a little bit of food coloring in each sort of spot. You're making like a triangle. And you have to open this one. Didn't realize it wasn't open. There we go. Done. Open this one up as well. All right. Good stuff. Oh, the balloon experiment's good. There's a few different ones with that you can do. There we go. Done. Okay. Now, I can see Kate's done her one. You're faster than me. Do it quick with one hand. All right, cool. So right now, the food coloring hasn't actually moved much. And the reason why is that the fat in the milk is blocking it from moving. Food coloring is water-based. There is a lot of water in milk, but there is also a bit of fat in milk too. Now, what we need to do is get ourselves some detergent. Doesn't matter which brand, though I suppose if you'd like to do variable testing, you could try different brands of detergent. But we're going to add the smallest of drops of detergent in the center. Let's look what the thing does. All right, moves outwards instantly. Now keep watching it. A lot of kids will go, oh, it moved outwards, and they walk away and they tell you, oh, it moved outwards, sir or miss. But there's more to it. Keep watching it, and the colors are starting to happen a little bit. They start to sort of swirl. They're starting to come on up a little bit now. Now, what actually happened is, yeah, there's the colors coming up now. They're billowing up. They're on their way up, and they'll start stirring. Actually, I'm just curious. Can we spotlight Kate's one? Because I can see it's up in view. We might as well see what her one looks like as well. There we go. Yes, happening your end. Now, your one seems to be static for a little bit too. Then is it starting to stir yet, Kate?
Kate, you're on mute. You'll have to unmute yourself. Yeah.
Yeah, it sure is.
Right.
The detergent is pushing the colors.
Yeah, absolutely. So here's what's actually going on. There are two things happening. Yeah, the colors are starting to come out for sure now. First thing, the colors went outward straight away. Now, the reason why is I love it. I love it in the chat there. The fats are emulsified, yes, by the alkaline detergent. That's the true answer. The detergent breaks up the fat. Now, if you break up fat, it's going to literally break up. And as it breaks up, water in the milk swirls to fill the space. And it takes the food coloring with it as it does it. And so as you try different, milks, you'll have different amounts that this will actually do. Now, if you want to look at the first part when the colors went outwards, another way of showing that is with a completely different bowl. So I'm going to move this off to one side. And get a different bowl. And this time, just pour some water in there. And we're going to get some ground pepper. If you haven't got pepper, just grab some dirt. Oh, thanks, Kirsten. Yeah, I'm hoping it's meant to be all done with really simple stuff. Absolutely. Okay, so we get our pepper in here. And you watch me put in too much, but I'll put in a little bit. There we go. A little bit more so you can see it in camera. Or a bit more. Done. Okay. Now, if I add detergent, let's do like we should do in science. What do you predict will happen if I add detergent in the center? I feel like I'm doing like product placement. It doesn't really matter. What will happen? What do you think? What will occur? Well, let's find out, hey? So I get my drop of detergent, drop it on in. It's pretty quick. Out we go. In fact, this experiment went viral at the start of the pandemic. It's like people you talked about as, keep your distance type thing. What's actually going on here is we broke the surface tension. Often the surface of a liquid is described on websites like the surface of a drum, where a drum skin is pulled very tightly. It's got to do with, well, honestly, forces between the molecules at the surface of the liquid pulling quite tightly compared to further down the liquid. Now, when you add detergent into the center, it breaks that tension and it sends the liquid outwards, and therefore the pepper outwards as well. That's exactly what happened with our milk at the start of that experiment too. It went out. Yes, absolutely. I can see someone mentioned about the coronavirus thing. Absolutely. Yeah, cool. Now let's do a little bit more. Let's keep our theme on bowl experiments. Bowl experiments are great. They're really good for small group work. And I might just quickly go to my face so you're not just talking to a table for a little bit. So I'm just going to change my view to my other camera. That one. I know some people are teaching where kids are still stuck at multiple homes by themselves, and you're like 1 to 30 different classes, which makes it challenging, right? But that also means that you can kind of, even if the students don't all have the materials, what you can do, just like I've been doing with Kate, is you can spotlight a student to show a thing, and then kids can comment to it. That can work quite well. Now, if you haven't set up multiple cameras, I might briefly show you what I've done. And then we'll keep on doing with some more science. Now, just to my side, over here, there is one camera here, which I still haven't used yet, just sitting on a tripod, and another camera on a retort stand because we're science teachers. But anything to hold a camera down is usually handy because you've got an above view. And if you needed to do a quick side view, you can then talk from here and go, hi guys, I'm going to talk this way and show you a thing and pick you up and look you around and whatever. That's really handy. And then you can go to the main one. Another thing that can be handy when you're presenting online with science experiments, it's really handy to have, if I go around like this, 2 TVs, not one, or 2 monitors. Because, as I talk to this one, because you can then put your websites and everything that you're sharing in one monitor, and then you can see yourself in large on the second monitor, so it's just easy to arrange stuff. Anyway, so we'll get out of doing that for a little bit. Let's go back over to my desk view. Okay, another plate experiment. This time, this one actually it's fairly well known these days, but in this case, we have a bowl, and we're going to get some water. Shallow amount, please. Oh, I didn't get enough. In we go. And then choose 3 different colored Skittles. Just curious. This will be fairly familiar to a lot of people. I'm interested to see who has done a Skittle and water experiment before, just out of interest. It's been around for a little while now. A few people, yep, they smile. Yeah, fair enough. Now, notice the colors are coming out. Now, I want you to have a think about, let's talk about the vocabulary kids will use when they're watching this happen. What words are they going to use? What are they going to say happen? Write as if you're a 13-year-old. What would they write? Or a 12-year-old or an 11-year-old? What would they write? Yeah, you're right, Kirsten. They'd say melting, leaking, spreading, dissolving. Yeah, bleeding. They're the sort of words they're going to use. Now, one of the ones I want you to be listening really carefully for is the word melting. It's not melting. Melting is changing. What are those balls? Those are Skittles. Yeah, the color is coming off. Melting is adding heat to a solid and having it break up and turn into a liquid. I'm not adding heat to a solid right now. What's happening is that the color and the sugar is dissolving. Now, in this case, the green, the purple, and the red Skittles all have the same amount of sugar in them. That's what they are. They're all the same. They're effectively the same thing. Now, what I want to see if we can predict, what do you reckon? If I get a pure sugar cube and I put that right in the very center of the plate, what do you think the colors will do? Will the colors go into the sugar cube, move away from the sugar cube, or do nothing? What do you reckon? What do you think? Into, go in, go in, go in. Let's find out. All right, we'll put it in here. Now, this is a patience activity. It's not as quick as the milk experiment, but it's starting. And we're starting to slowly see the result. The camera takes a little bit of time to pick it up, but look around the edges of that sugar cube. Now, by the way, I have seen people strap a camera that can zoom in and out above on a ceiling. That's really cool if you got one. We don't have that sort of budget, but you can do it. This goes down. Look at what's happening around the edge of the sugar cube. The colors are moving away. So, why? Aaliyah's got it. You want to go further with that word, Aaliyah, osmosis? What do you want to say? Do you want to go further with that? Up to you. You don't have to. Oh, yeah, Shami, you're right. The sugar cube is more concentrated. Yeah, concentrated. There's more sugar there. There is far more sugar there than there is on the edge of the bowl. And this is, like Barb said, truly a concentration gradient. Sugar from the middle, going from high concentration to low concentration. And it pushes it out all the way out. It works really well. Okay, so let's just quickly sort of change up what we're doing a little bit. I'll just go back to there we go. All right, good. So that works pretty well. And you might have seen what the experiment that went viral, I think it was about a year ago, where, well, no, it was 2 years ago, where people would put a ring of Skittles around the edge of a bowl. Do you remember seeing that? and then they'd add hot water to it. And you get this rushing of rainbow going into the center of the plate. And that was, again, a concentration gradient. It was a lot of sugar on the outside, moving to where there's less sugar. And because you had oh, good, you like the lung experiment. That's cool. Thank you. So I do get distracted by the chat. But what's happening with the heat of the water is you could repeat that same experiment that I just did before. Adding heat to any chemical reaction makes things happen more quickly. There's more energy. Now, how about we do a little bit on heat? Just because that seems like a segue. I've got stuff all over my table. So let's do a quick one, which can sometimes bring out different answers to students. So here we go. Let's go down over this way. All right, so back to my hand view. Now, I want to get a candle. There we go. And we're going to light our candle. Just be aware of your smoke alarms, your fire alarms, wherever you might be. Let's not have the fire department come to you during this session, just in case. Okay, so we got it burning away. Get going. It's only just doing burning a little bit. Okay. I might have to use a different one maybe. Now, what I've got is a couple of different balloons. Firstly, let's get a normal balloon. And I'm going to blow it up. Done. Oh, there's a hole in that balloon. Don't you hate that when your balloons do that? That's why you always have spare balloons. I'll have to use another one. All right. Next, we'll add it onto there. What do you predict? It's pretty easy. I mean, what's the thing going to do when I add it to the fire? It's going to pop. Yeah, it goes. Why? Why does the thing pop when you add a balloon to a candle? And by the way, on an online point of view, you should be doing that demo, not the kids playing with fire, because you can't stop them from burning their house down. But I mean, yeah, the heat made the air expand, 100%. The air expand rapidly, and the latex of the balloon couldn't handle the amount of heat, and it ruptured. Cool. Let's change the experiment. Water balloon. So let's go down to view closely again. There we go. And we'll get it nice and set up again. Get it lit up. There we go. Okay. Versus into the water. In fact, some kids think I'm not touching the flame, so we show them. Absolutely we are. It is working. Now, the way it works, this balloon is acting like a heat sink. The water absorbs the heat really well. It conducts the heat incredibly well away from the latex, and technically does get slightly bigger as it warms up, but it's taking the heat energy away from the latex, and so the thing doesn't pop. Though I must say, and be honest, how many of you just going, kind of just burst, I just wanted to burst on you. Come on. I was that kid. All right. So anyway, it does work. Now, if you wanted to use this as a little bit of a model, yeah, I love that question. Does it heat indefinitely? Seems to me like a science experiment. Why don't you set up that exact, I mean, when things go to normal, and you've got your students in your rooms, like some of us have it, some of them don't. Why don't you set some balloons sitting over some candles, looked after carefully, and just see how long it works. It's going to be longer than a couple of minutes, I can tell you. Now, yeah, they want to put other things into the balloons too. Yeah, they could try that. In fact, you could try, does it matter if you have sugary water or salty water? If you change one thing and see the effect, you are doing true science. You are changing a variable. Now, a lot of kids will think that no result means they messed up somehow. But they also need to learn that a null result is still a result. It's still, that's what happened. So they're still going to just learn to go, this is what I report. Nothing changed. Cool, that's the answer. All right, so I have also used this to talk as an analogy about if you got heat going up there, the water does expand and some of the heat goes upwards. So it's taking the heat away from there. And if it cools down, it's then going to drop down again and then heat up again and then go back up again. We're sort of getting a mini convection current in there as well, only slightly. Now let's briefly do a convection current. I just feel like doing a teabag rocket. You done teabag rockets? Teabag rockets are good. They're good fun. All right, I'll do it. All right, so tell you what, we'll go like this. I'm going to get, as I go over here, a bolt. There we go. And I'm going to put my bolt upside down like that. I might go in closer so you can see a little better, actually. There we go. And I've got in here some tea bags. Now, I know tea bags are different in every different country, and I know we have different flavors of tea that we like. All that matters is that your tea bag has the ability that when you cut it opens up into a wide cylinder. Let's find out. So currently I'm using English breakfast tea by Twinings, but there are other ones. I'm going to cut this off like this. Some tea bags that don't have the ability to open up like that will never work. They'll usually have a heat press seal right in the center. They will not work. You need to have a column of air inside your tea bag. So you flatten your tea bag out, your tea leaves out, so it's like a bit of a launch pad. And then you put your tea bag, sometimes it falls over on you, just like that, lightly on top. Now, before I light this thing up, think about the tea bag. The tea bag, I know in this camera you can't see it so well, but there are holes in the tea bag. I can see Kate setting it up, good stuff. Now there are holes in the tea, and your one actually should work. Now, that means air can pass through the tea bag just like tea can. So I'm gonna go with this. And I feel like, because I should be showing best practice, I suppose we should be wearing glasses. Probably should. All right, so on we go. How many of your students do you find wear their glasses up there? Nearly every one of them, right? And you're forever telling them to say, you're not protecting your forehead, put them on your eyes. Anyway, right. So this is when I mess up. This is why it's great that Kate's got a setup, because if mine goes wrong, she can do her one. Because sometimes it tips over on you when you don't need it to. But we've got it set up as best we can do for now. I'll tell you what. And we're going to light it up and see if the thing will go. I shouldn't have touched it, should I? Okay. I may even have to keep it upright whilst it falls down. We'll see how we go. So we'll light the top. We'll let it burn downwards. There it is, one to the tip. Stay upright. And up we go. It went and hit my roof. And now it comes down with the ash here and the ash there. And there's Kate's going. Did it catch on the tea bags? On the tea leaves? I think it did.
It did not go up.
Yeah, that's nearly always the fun. If you press the tea bag in a little bit, and I'm telling you, it's only slight. You push it into the tea leaves. The tea leaves grab on tight, and the thing won't let go. But yeah, that goes. So let's explain what was going on. Hey, now by the way, just because we're doing a global event in Sydney right now, there is a thunderstorm coming over the top of my space right now. I'm in a soundproof room, but I heard it just, which means if I cut out, that's why. All right, so we'll keep on moving on. All right, really quickly, a quick drawing, because yes, we can do experiments, but I'm also sort of looking at like different ways you can teach science. Please have a whiteboard around. I know in Zoom that you can share screen, then go to whiteboard. That's totally a thing you can do. But I must say, I'm still a little bit old school. I do like being able to go quickly. There's my plate. There is my plate. And we had fire on top. Now, what was happening was the heat went upwards. That's what air does when you heat it up. It expands, gets lighter than the air around it, and up it goes. Now, remember the tea bag has holes in it? That means that as the air here rises upwards, you're producing a low pressure area because the air is leaving that space. That means air here goes through the tea bag. Air here goes through the tea bag to fill that space. but then it gets heated up and they go upwards too. And so what you've got is this convection current, this big current of air rising up. And I know it's off camera, but my TV honestly hit the ceiling. It's about 2 meters above my head. So you'll often see with bushfires, a big column of hot air rising, and then all the moisture starts to condense at the very top, and you get like a cloud at the top of a bushfire. And the T-Bay is kind of like a really quick way to talk about that. All right, are you going for it again, Kate? Why not? Let's just see if we can get.
So what my issue is that I'm using, because I have no matches, I lit my candle on my stove. So I think the issue was that wax dripped onto the paper.
That makes it too heavy. That'll, yeah.
So now I'm wondering what I can light on fire, maybe a chopstick, to get this. So I'm super curious here. This is my third attempt while you were talking. So now I'm going to try it this way.
I love your work, because that's now worked. Except it's now tipped over. Watch your fingers.
And not success.
No, that was going to work. You were totally on it. That was ready to go. In fact, after this session, you totally can do it. Now, I didn't set this up. I don't have any of the materials here, but I do want to suggest another really good thing that really hammers a misconception with heat transfer. You know how you can get a metal baking tray, and you know how you get those rubber ones? So metal one and a rubber one. What I want you to do with your students is get them to feel the metal one and the rubber one, and ask them which one feels colder. Now, make sure you say the word feels. Which one feels colder, the metal one or, silicon. Is that what it's made of? Yeah, silicon rubber, those guys. So you got metal or silicon. Now, when they touch the metal one, so their hands on the metal one, it'll feel cold. When they touch the silicon baking tray, it won't feel that cold. And then you ask the kids, righto, well, what if you get an ice cube in each? One on the metal tray, one in the silicon tray, rubber tray. And they're sitting on the desk. Which one will melt the ice first? And the kids, even when they're kind of used to you messing with their head, they will go, well, the hot one, the silicon one's going to melt it faster because it feels hotter. And yet the metal one melts the ice faster, even though it feels cold. Now, the reason why is that metal is an incredibly good conductor of heat. So if you've got a silicon baking tray on the table and a metal baking tray on the table, the metal baking tray will draw heat up off the table and into the ice cube. And it's so good because it shows kids that start really questioning, well, what do you think heat really is? Because when you put your hand on the metal tray and the silicon tray, the reason why the metal tray feels like different, the reason why it feels colder is heat leaves your hand into the metal tray. So if heat's leaving your hand, you feel colder. And just reading now in the chat. Yeah, that's right. Donovan, yeah, I get that. That's exactly it. Cool. All right, so let's, we've only got a few more minutes left. Now I do have, seriously, I've got heaps of stuff here, but I just want to just quickly go, because we've got, everyone's here got teaching all sorts of stuff. I'm just curious to see if anyone's got any quick questions about, hey, I'm teaching this particular unit. Is there a particular experiment that might help out? What do you reckon? Yeah, you're using Tetley? Yeah, Tetley doesn't go too badly. All right, so what are you thinking of, right? Let's do another one quickly. How about we do a little bit on friction? A little bit on friction. So now if I was doing this as performance science, like making a thing of it, I'd do this in front of everyone to make sure I'm not cheating. But for speed, I've got inside here, I'll go in close, just a bottle of, well, rice. You could pour it in with a funnel so the kids can see you haven't got like glue in there, but it's just rice. Right, what we're going to do is we're going to just look at friction in a very simple way. You need yourself, well, a pencil. And you open your bottle up. You watch me drop this everywhere. But you open it up and you push your pencil in, but you're going in at different heights. And you do it lots of times. Lots of times. Now, as you do this, you're compacting the rice and you're pushing some of the air out of the way. and more rice is touching the pencil, the more you do this. Now, eventually, actually, I'm going to get a longer pencil. That one's a bit short. There we go. In we go. Eventually, it grabs on. Now, you can you just sort of just feel when it's about to do it. Oh, it's close. Oh, it's so close. Come on. Now, while I'm pushing this quickly, we had a question there about how to rockets to take home. Have you made a, oh, that's close, a bottle rocket, a water rocket? So get yourself, you can usually get a rubber stopper or a connector that goes onto a bike pump. Put that onto a bottle, like a bottle with water, half filled, and then pump up the air and the water inside your soft drink. Oh, it's going to grab. I thought it was going to do that then. Oh, this is a new setup. It's about to do it. You can see it's starting to grab it. Are you going to do it? Am I going to fail? Hey, by the way, one thing that is important to do when you're doing these experiments is it does not matter at all if you have a quote unquote fail or something not work. You just got to either persevere with it or explain what's going on. In this case, it is getting close, but it needs a bit more compacting, to go. It might be slightly shorter rice. It's trying to grab. I can feel it. I might go right in. Is it going to hold? Nah, it's not going to do it for me. All right, next one. Oh, there you go. Bottle rocket. There you go. Really quickly, there's another one. Have you done a film canister rocket? Now, film canisters are harder to get. We don't have cameras to film anymore, but you can still get film canisters from eBay or Amazon or one of those sort of places. And what you can do is you put vinegar and bicarbonate soda in it. Like wet your bicarb soda and put it into the lid of your rocket, then turn upside down with vinegar in it and off it goes. Just make sure you've got glasses on or it will really go. Is it going to hold? Nah, struggling. I'm not going to be able to do it today. You kidding me? Oh, no. It was so close. Okay, let's do another quick one as well. How about we look at another misconception, because I'm struggling with that. See if you can report back to us to see if you get the thing to go. Let's do one. Yeah, it's trying to grab the pencil. It's just, I've got to do it for a lot longer. I don't want you all sitting there waiting for me to try and do it. All right, so how about we do a quick one, which all of you can do no matter where you are. I'd put money on that you will have a book somewhere. And I reckon you'll have a piece of paper somewhere. What we're going to do is we're going to investigate gravity. Now, I'm really throwing this out at you like, hey, you didn't tell me to have this ready. But nearly always someone's got a book and a piece of paper. All right, so I'm going to get my book, got my book and a piece of paper, and I'm going to cut my piece of paper so that it is the same size, roughly. So you just want the same size piece of paper and the book. Right, here's what we're going to do. I'm going to change my view. So all the way up. Now, this is where you can kind of see the floor. Here's what we're going to do. So go find a spot. Sonia's getting ready. All right. So go find a spot where you're not going to knock your computer or something. Yes, Donovan, you're totally right about interlacing two books together. Telephone books work really well. Absolutely. And you pull them together. The Mythbusters tried to pull the two telephone books apart with a tank, and they couldn't do it. There's even a guy who has bungee jumped with two books connected together. Crazy. Anyway, so let's do this. So get your paper, get your book, and now everyone drop them at the same time. Ready? 1, 2, 3, drop. So what are the students going to say? They're going to say the book fell faster, which it did, and they're all going to say that the book was heavier. Yeah, that's what they're going to say. So let's change what we're doing. Get your paper, get your book. Now get your paper and place it on top of your book. And now drop it again. 1, 2, 3, drop. They drop together. Why? Why is that the case? What do you reckon's going on? Now the kids will say it's a bit unfair because the paper's on top of the book. It's dropping down. All of the air is hitting the book and it's not hitting the paper. And just like you just said, the book is breaking the resistance of the air. Absolutely. Now, let's now finish off this exploration. Take them apart again, but this time screw up the paper. Make it into a tiny ball. And now put them either side again. 1, 2, 3, drop. Same speed again. So here's what's going on. It is about air resistance. When this paper is open, it catches more air. Now, let's be honest. When I cut it, it was the same size as my book. Of course, the book is heavier, which means it's got more force, so it can push through the air better. The air resistance is a problem, absolutely. But as soon as we make its surface area smaller, it has less air resistance for it, so it can now fall at the same speed as the book. Now, you might remember the experiment that was done on the moon. Look up this after this session's done. Go onto YouTube or your favorite video thing and look up Apollo, hammer, feather, drop. Apollo, hammer, feather, drop. And what happened was one of the Apollo astronauts dropped a hammer, dropped a feather on the moon, and they dropped at the same speed. And it's because there's no air resistance on the moon, which is fantastic. In fact, if you really want to get a bit fancy, which we're not doing with 3 minutes to go, you could actually use a countdown timer on the YouTube video, throw it into some calculations and work out it was actually done on the moon for sure, because at the speed it fell at and at the height of that particular astronaut, there is no way that was done on Earth. It was done on the moon. But anyway, it's a really easy experiment to look at gravity. Most kids will absolutely swear to you that heavy things fall faster. Another experiment was done, it escapes me right now, BBC science guy, it'll come to me really soon. Sorry, I know there's a recording. I should remember his name. But they dropped the bowling ball and a feather and some other bits and pieces in a vacuum tube, a huge one, like 30 meters long or something, and it did the same thing. Cool. All right, so last little bit more. Dear. So I might just quickly check. Oh, good. Thank you for saying thanks, everyone. Now, I know this session's about to finish. Again, I'm going to put this link again in the site in case you missed it. There really are, and I know I can feel like self-promotion. It's not at all. It's just generally this. We've written this over, gosh, 16 years, which is people just wanting to say, hey, have you got experiments about so-and-so area? This link will help you so much. We're doing different experiments throughout the time. Now, I hope you've enjoyed the Learning Jam sessions. This was just a bit of fun. Now, if you had a bit of a take home for these particular sessions, this particular session is firstly, online science does not have to be read a book, now talk about it. Now they're important. We've got to do chapter reading too, but there's no reason why they can't do experiments in their site at all. Just think about, is it safe? Can they get the materials easily? And what's the effect of doing those experiments if something goes wrong? And be cool with if it goes wrong, doesn't matter. If you can, consider having a secondary camera. It does help, especially with an above view, it totally helps. And have a whiteboard or something to just write like you've always done in class anyway. Yeah, so I just thought, is there any comments from Pareda or any of the Toddle team?
No, I think this session went by too fast. It was amazing. Thank you so much, Ben. Thank you, Kate. Thank you, Jonathan and Sonia, for actively participating. Kate, it was great to see you keep at that experiment regardless of failing many times. So thank you so much. And Ben, we've put in the link again. I'm going to drop the link again to the 150 resources, the 150 learning experiments, so that everybody can go check out the incredible work that you're doing at Fizzics Ed. Thank you so much again for making time. Everybody else, please go to the next session, which is a personal well-being session. It'll be a great break while Ben keeps at it for the experiment. Thank you so much, guys. Thank you.
No worries. Thanks so much. I'll keep doing this for the rest of the evening. See ya.
Bye-bye. Thank you, everyone.